we can revisit some of our commutation relationships and commutator operators with our Dirac notation. And so let's do that in this segment. Uh, well, for one thing, in Dirac notation, we write the Schrodinger equation like this. It's sort of almost like a vector. This is a state vector over here, and we have an operator on it, and we get that the Schrodinger equation is IH bar times the time derivative of this vector, state vector, is equal to this Hamiltonian operator applied to the state vector. Uh, that's identical with, if you remember, this expression where we had the partial derivative. The thing is, in a certain sense, this equation here, we're looking at the x component of it. So that's this x piece. Yeah? And this derivative, we don't differentiate with respect to the component. We just take the derivative of, and so usually we represent this with a partial derivative. On the other hand, we had this operating on this, and this operator can make linear transformations of the components in the finite space. So in any event, this is sort of the matchup that one does in Dirac notation. In the sense that we're looking at the whole vector as a whole, so this is like a vector equation, and this is like a component equation. Well, as we've seen, one of the important things that we need to look at is the average values of the expectation values and the derivatives of expectation values. And so you'll often see this notation. These brackets here indicate we're looking at the average value of the time derivative of some physical quantity. And in quantum mechanics, this thing basically means this. I have to have a Hermitian operator for whatever this quantity corresponds to, and I have to sandwich it in between a psi, it's the psi for the state, yeah? And that's just sandwiching it in between these two, and then taking the derivative of that average value. So you'll see this notation sometimes probably better to write it in this form. Yeah, but you see both. Sometimes you'll even see this. They'll put ddt of this expectation value of the operator as this quantity here. And the way you do that is is simply to take the total time derivative of each piece in turn. So essentially you use the product rule. The time derivative of the first vector plus the first vector times the derivative of A, and I'm going to assume that A depends on T, and usually on this side the summation over X is not done here but is done on the brackets. So the partial derivative and the total derivative of A are the same times this piece. And then finally, using the product rule, you have this piece and this piece times the time derivative of the last term, which is here. So one essentially uses the product rule on this in terms of these each term. And then you just make the identification from the Schrodinger equation. I can divide both sides by IH bar. And I get this as another Schrodinger equation. And everywhere I've got a ddt, I can put that in. You can take the Hermitian conjugate of both sides of the Schrodinger equation. When you do that, you just get the reverse order, remember. But you have to, if I take the Hermitian conjugate of this side, it becomes this. Hermitian conjugate of this side, it's reverse order Hermitian conjugate psi. But I also have to replace I by minus I, and so you pick up this minus sign. And then, since the Hamiltonian is a Hermitian operator, this ddt of the bra representation of psi is minus 1 over IH bar times psi times h, since I can replace h by h dagger by h. And now just plug all those in. Put these two terms in. See if I can get both of these in here. So for this first term here, well, that term is this one, so I replace it by this quantity here. So I replace it minus 1 over IH bar, that's all of this, times times psi times H, and then A and psi stay the same. This term stays the same. Don't have any change there. And the last term, which is this one here, I replace dt of the ket vector. Well, here it is right here, so I replace it by 1 over IH bar. So 1 over IH bar H times the ket vector back again. And then I can combine terms. I can, well, the order is sort of immaterial, but this term is going to have a minus HA, so I have a minus HA that I combine with this one over here. I get a 1 over IH bar AH, so that's this term, and I subtract this term from it, and then I have to add this term here. All of this sandwiched in between the sides. And if you remember, this is nothing more than the commutator of the two operators. It's A commutator H, where I define the commutator to be AH minus HA. I've still got my 1 over IH bar, and it's sandwiched in between these two. And then we're back to the sort of standard representation. The time derivative, the time rate of change of a quantum operator is just the partial derivative of it with respect to time, plus 1 over IH bar times the commutator of A with the Hamiltonian of the system. So in a certain sense, the Hamiltonian helps to generate the time dependencies of operators. And then, of course, we define the commutator, this bracket symbol here is just the A times H minus the reverse order. It's a measure, again, remember, of how close these two operators are to commuting. If this is, in some sense, relatively small, then they almost commute. But if it's large, then they don't have any, they don't commute to any degree. Usually, uh, the quantum operators themselves do not explicitly depend on t. That's not always true, but is often true. And for us, I don't think we'll encounter any in which it's not true in this class anyway. And as a result, this first term, if A doesn't explicitly depend on the time, then the operator, then that goes out. And then we see that in that case, the vanishing, if the two operators commute, then I've got a 0 here, and A doesn't depend on t explicitly, and these commute, then I get the time derivative of this operator equals 0. And if that's the case, then we would say that the operator A is a conserved quantity. So you get these conservation laws from this particular form. Well, sometimes people call this operator equation the generalized Ehrenfest relationship. We actually got it in another much more lengthy way. If you go back and recall that and look back in those portions of your notes, it took major effort, a couple of lectures to generate that equation, that formula. Because we had to do everything in component notation. And here we're essentially treating these like vectors, the state vectors, and these become like matrices that we're dealing with. Well, to give you a quick example of an application, let's take a look at the time derivative of the quantum mechanical position operator. And remember, in the position operator, it's just replacing the coordinate with the coordinate itself. And it obviously doesn't explicitly depend on time. And x and t are independent variables, and so this partial derivative goes out. And so we immediately get like the usual fashion that it's just as this commutator portion. For the standard case, we're in one dimension where we have momentum. The Hamiltonian becomes momentum operator squared over 2m plus the potential. And that's for a particle of mass m moving in a potential energy V. We have this. Now, the commutator of a sum is the sum of commutators. So it's sort of a distributed law of this commutation relation. So this term in brackets here, if you write it out, I have the 1 over IH bar, but it simply becomes the commutator of the first piece plus the commutator of the second piece of whatever the commutation's with, which in our case is x. And then now we can do the same trick that we did earlier. What I would do is write this out in the commutation. There's got a factor of 2m. It'll come outside. It's just a constant. And the commutator is x times p squared operator minus p squared operator operating on x. And over here, a similar thing. I get x, but remember, it's just a multiplication, v of x minus v of x. But these now are just numbers, and so they obviously commute. So these two are the same, and so they go out. And we're down to just this first term. And then I write these out. Actually, I write this one out here, and this p squared x, I write it out. Where did I write that one out? I wrote that one out all the way at the end here, minus p squared x. And then in between, I add and subtract pxp, minus pxp plus pxp. Order's important, but I'm adding and subtracting the same term, and so I'm essentially adding 0 in this particular term and these two middle terms. And then I regroup the first two to be here. I do that. They both have a p on this side, so I can pull that out. They are associative, and so I can pull it out, and they are distributed from the right or left. So I get this. I do the same thing for these, except now I pull the p's out in the other direction. So I get x p. When I pull the p all the way out, I'll get px over here. Or writing those expressions out, this is nothing more than the commutator times p. And the p, and this is nothing more than the commutator xp here. I know the commutation relation between x and p. It's the commutator of position momentum is just IH bar. And I've got two identical terms. So I simply write those as 2 IH bar P. And I get the 2's go out, the IH bars go out, and I get just 1 over m and a momentum operator. And so one gets the operator equivalent of the velocity being equal to the momentum divided by the mass of the particle. Well, again, we've done a similar thing, but it was a lot easier in this case when I don't have to do a bunch of integrals and explicitly evaluate everything on both sides.